Thanks everybody for wanting me here today. So as Sunshine alluded to, I've been thinking about acidification for a while, and I've been thinking not only about the chemistry of it, but I've also been thinking about how we talk about it, because nothing bores people faster than chemistry. It's kind of funny. So I'm going to talk to you a little bit. I'm going to give you sort of the very, very treetops view of the chemistry today. And you can feel free to ask me questions about the details afterwards. And then I will talk a bit more about how we actually find success in talking about ocean acidification. And you can kind of keep those ideas in mind as the other speakers come through and think about, how to find that story in there. So first of all, what is ocean acidification? The IPCC defines it as a long-term decrease in ocean pH and carbonate ion level, and it's caused by uptake of carbon dioxide from the atmosphere. The IPCC definition is actually a bit broader because it also allows for other chemical additions and subtractions to the coastal environment. But the long story short is that we are emitting carbon dioxide into the atmosphere, and about a quarter of that makes it into the ocean. And at the same time, there's a lot of coastal processes that cycle carbon dioxide through the coastal environment. So when we emit our carbon dioxide into the atmosphere, which is what you see happening here with this red trace, this is carbon dioxide rising in the atmosphere from 1960 to 2010, we see ocean pH dropping because when you put carbon dioxide in seawater, it creates an acid, which lowers pH, and it sops up carbonate ions that the organisms need to form shells and skeletons. And then the blue trace here is the seawater carbon dioxide concentration, and you can see that that's rising right in step with the atmospheric level. So we're quite sure that this is happening. We've got data around the world that really shows clearly that the atmospheric carbon dioxide rise is resulting in progressive changes in ocean chemistry. So what happens even in the coastal zone where I alluded to all these processes that are changing the acid-base balance? It all boils down to two chemical equations. And what we have happening here is when we dissolve carbon dioxide in water, it releases hydrogen ions. And remembering way back to chemistry class, those hydrogen ions are what we measure when we measure pH. And so we have carbon dioxide plus water gives you hydrogen ions and what we call bicarbonate ions. Now at the same time, some of these hydrogen ions scavenge carbonate ions from the seawater. So that's how they're sort of sopping up those carbonate ions. And they're leaving us with even more bicarbonate. And the problem with that is that organisms really struggle to form their shells and skeletons when there's less carbonate ion in the water. So this is actually driving the ocean, these processes, these products of these processes are driving the ocean towards a place that is less hospitable for marine life. And they manifest many consequences. I think Whitman will probably talk about this in terms of shell building, but also changes in pH will change life processes. It changes the fertilization success of some organisms. It changes the respiratory efficiency of other organisms. So there's a whole host of biological changes that can follow from these two fundamental chemical changes driven by ocean acidification. So forecasts that we can do with three-dimensional coupled ocean models show that carbonate levels in the ocean are predicted to drop with time. So here on the left is the year 2000, the middle is 2050, and the right-hand side is 2099. And this assumes the business as usual carbon dioxide emissions scenario that we often talk about that the IPCC traced out a few years ago. And this business as usual scenario basically suggests that we're going to have very rapid industrial development with the years and very little in the way of carbon dioxide emissions mitigation. And so as this happens, what we have is the carbonate levels dropping. And what I want you to kind of keep an eye on is this sort of red area, the reddish-orange areas. They are increasing from the poles towards the equator. And these red areas are areas that are unfavorable for carbonate structures. So these calcium carbonate shells and skeletons I mentioned are really going to have a hard time remaining intact in these red areas. And you might say, well, that's no big deal because I know that coral reefs that use carbonate skeletons don't occur in the polar regions. Well, those are the tropical coral reefs. There's actually cold water coral reefs that you find elsewhere in the world that are nurseries for a lot of finfish. We don't fully understand the role of the cold water coral ecology or the ecosystems in the whole ocean ecosystem yet, but this is an environment that is sort of not well understood, but certainly at risk from this process. And at the same time, as these sort of the favorable area squeezes down towards the equator, we also have to remember that temperatures are going to be rising at the same time, and they're going to be rising at the equator fastest. So you kind of have a disconnect of favorable territory for many marine organisms that are sensitive to both temperature and chemistry. So at the same time, near shore is where we're really concerned about, because we have lots and lots of economically and culturally important marine resources near the shores. And in the shore area, we have not only carbon dioxide from industrial processes entering the ocean, but we also have a number of other things happening that can also adjust the sort of acid-base balance of coastal waters. We have things like nutrients running off from agriculture and I guess you could even just say, people's lawns and things. And those are adding to the overgrowth of algae in our coastal regions. And the algae photosynthesize and breathe out carbon dioxide. And they photosynthesize to bring in, to create oxygen and fix, but then when they die and settle, bacteria eat them and release carbon dioxide. So these can be major, major influences on the overall carbon dioxide balance of coastal regions. We also have things like upwelling of low oxygen, high carbon dioxide water. And in the Pacific Northwest, we have an instance where we know that ocean acidification contributed to the mass mortality of oyster larvae for about 4 years running. And that the outcome, or the reason for that, was because we had the combination of upwelling, which is pretty common on the Pacific Northwest coast, but the upwelling was enriched with this high carbon dioxide water that was basically sort of accelerating ocean acidification for that area. At the same time, we also have smaller components from things like pollutants that have acid base characteristics to them, which may also change coastal pH. But that has been a problem in various areas of the nation over the past several decades with different local coastal pollution issues and acid rain and things like that. So you can see that in the coastal region, we have a very complex system. And so in addition to just the straight up carbon dioxide entering the ocean, we also have mass amounts of recycling that's happening. And so lately, the scientific conversation has been focusing more on coastal acidification as well. And coastal acidification is sort of a catch-all term that incorporates not only the invasion of carbon dioxide from the atmosphere into the ocean, but also the role of upwelling, biological activity, the respiration and photosynthesis that naturally happens, runoff from the land, mixing, exchange with sediments. And in the Pacific Northwest, we know that air-sea exchange and upwelling were really the major contributors to the acidification event that was so harmful for the oyster industry out there. On the East Coast, we haven't had a similar sort of smoking gun event yet, but we think that the likely factors at work on the East Coast are going to be more the issues that are sort of very close to shore, things like river runoff, groundwater discharge, and the high amount of photosynthesis and respiration that happens in our highly developed, somewhat urbanized coastlines. So now I'm going to change gears a little bit, and I'm going to say, since we've had this very sort of quick introduction to the chemistry of ocean acidification, and I haven't lost you, which I'm super grateful for. Everybody's nodding and looking down and taking notes. I feel really good. But one of the problems that I anticipate you will have as folks who are trying to talk about ocean chemistry to other people is that the top one is most people really, really don't like chemistry. That actually was something that pushed my own research towards impacts on humans, because it was so darn hard to talk to people and get them excited about pH. So it's very hard to make this concrete also, because generally these changes are sort of invisible, and you have to kind of take it on faith that there's carbon dioxide cycling in and out. And if you're not in the thick of it, measuring it yourself, it's very hard to understand. It's a little bit less easily grasped than something like overfishing, where you're just taking lots of fish out of the ocean, or nutrient loading, where you're getting lots of green water because you're getting this algae overgrowth. So that's one of the other challenges. And then things, especially things that are driven by sort of global changes that are long-term, especially related to carbon dioxide emissions, it always seems like somebody else's problem. Everybody feels like, oh, well, I can't do anything, just me alone. I can't do anything to change this. And without some other action, then anything I do is for naught. And that's actually not really true, because in these coastal zones that are so complex, every little bit helps. Every little bit of adjustment that we can avoid to the acid-base balance in coastal zones will help those coastal communities, the ecosystems, be a little bit more hardy when it comes to facing what's happening, ocean acidification. So what we can say is we have a couple of don'ts. So we don't want to dwell on chemical reactions. We don't want to ignore that coastal zones are complicated. And we don't want to lose sight that anthropogenic CO2, carbon dioxide emissions, is a big piece of it. But what we find that really works is that successful messaging about global change, especially acidification, makes it local, so next to home, immediate, something that's happening really right now, and something that's actionable, that we can actually do something about. And so when you make it local, this is great, because these sorts of questions are exactly what journalists need to have to make a hook, to entice people to read their piece. So if you make it local, you can say, is a local waterway affected? How about key resources at risk? And how does this plug into other things? I was just talking with Whitman about the Chesapeake Bay situation, and the Chesapeake Bay is so accustomed to thinking about nutrient loading and all of these multiple things in the Chesapeake. The conversation is much farther along in the average citizen's mind about what's happening in the Chesapeake than might be elsewhere. So when you make it immediate, we have to think, okay, what's happening today? And if there's not a clear impact happening today, it might be the lack of knowledge that's your story. We might not know enough about these ecosystems. And then we have to also make it actionable. We have to think about if there's a fix for any of the drivers. Are we missing knowledge that we could actually pursue soon? And are there any workarounds that we could implement to decrease the impacts? This is actually a photo of some of the activities surrounding the Washington State Blue Ribbon Panel, which was convened to address the issue of ocean acidification. And it was in part a sort of a study panel, and in part a search for solutions. And the group came up with a list of actionable items that the state could pursue to begin to address ocean acidification in the meantime, while other, local and regional and national entities focus on cutting carbon dioxide. So the quick takeaways that I want to leave you with are that ocean acidification chemistry is pretty boring, but it's kind of a necessary evil to kind of understand the story and explain to readers. But again, a little goes a long way. Environmental problems and natural resources are always colliding in coastal zones. And coastal zones are very, very complex. And I think that makes for an interesting story, but it also makes for a hard story to tell. It's hard to figure out where the story ends and what is like for next time. And then finally, to tell good stories about ocean acidification, it involves local, immediate, and actionable pieces. And so, if one were going to be telling a story about the chemistry of ocean acidification, I'm thinking your most interesting hook might be to focus on why the heck is a chemist so excited about doing this? It's more of a human story about what keeps them going every day in the face of this, big possibly thankless seeming task. So those are my comments for you today. I'm probably just about out of time. And are we going to save questions for after? Are we going to? Okay, I'd be happy to take any questions you might have.